we're Germans, it's 50 on clock, we're on time. So we have to move on.
So we are happy to be here. My name is Michael.
I'm Florian.
And we try to show you how to build a DIY second generation quantum sensor within a quantum FabLab. But of course we start at the beginning. And we have a WhatsApp group, so we will, for example, put this on the WhatsApp group. So if you copy this, you will get the material.
So also afterwards, we will be very interested to stay in touch with you guys, because we are building kind of experimental stuff at the moment, which is becoming a project in the future. And if you are interested in what will be coming out from this process, we would be very happy if you get see ones of you which are interested to stay in that WhatsApp group, so we can stay in touch.
So what we are is on the one hand a normal FabLab and the first quantum technology FabLab as we know in the world. So we try to do DIY quantum technology. And what is our aim or our vision? We want to build a low-cost, repairable and enhanceable ecosystem for quantum sensors of the second generation. And some parts of this ecosystem you see here, I will explain later on. But at first I thought, because we had a small group, but perhaps we could do it really quickly. Who are you? So why are you interested in quantum? Could we make just a very short round?
Yeah.
Please.
Tony and Michael from Chattanooga, Tennessee. We have the largest amount of educational fab labs in the world in our system that we have in schools in quantum. We also have the fastest internet in the world in our city, and they're building on the quantum system, and so we're here to learn more about it and be able to use it with our students in the future.
We have quantum node. Yeah.
So hi, my name is Marcelo. I'm from Indonesia, but I live in Germany, and I've been working with open source machines and FabLab 2.0. So maybe I can learn something from Thank you.
So I'm Daniel Stein from Brigham Young University. I'm interested in everything about this, but in particular we do levitation, and this is an application of optical levitation that we'd like to explore.
I'm Klaus from a small maker association in Germany. We are kind of went into this weird quantum stuff, and so I'm always interested in seeing something really working with quantum technologies.
I'm Heaven Whitby. I'm the manager of the Fort Valley State University lab in Fort Valley, Georgia. And I don't think anybody in my area knows anything about quantum, so I'm hoping to bring it there.
So hello, I am Siddharth Kulkarni. I am an electronics engineering student. So during my first year in engineering, we studied a little bit about quantum physics, and I also like electronics. So the sensor part comes in. So both of these things are of interest for me, and I look forward to the.
My name is Sonam, and I'm also an electronic and communication engineering student at CST, and I'm looking forward to the quantum computing part, quantum sensors part, because it might help me in my final projects.
My name is, I started working at the FabLab Puebla. Hope you all guys will be in Mexico next year. Just a brief announcement. And we have large engineering schools, so I'm interested in knowing what is this and how might we use it in the future for our students.
Hello, my name is Joan Rai, and I work in Super Apple, and I'm electrical background. So I'm very interested to know about this quantum sensor and
Hello, my name is Josep. I'm from FabLab Barcelona. I don't know much about quantum sensors, so it will be a nice introduction.
I'm Dylan. I'm from Hong Kong. I study in Boston, Massachusetts, and I'm interested in quantum sensors because I'm heading into college, and I feel like this is an interesting sector because there's so many different like with microscopy or communication technologies, like quantum sensors can be used in so many different types of aspects.
Hi, my name is Karen Shetty. I'm an electrical engineering student from CST. I'm really interested in this session because I want to learn about it and hopefully find some ways to do it in the future projects.
Hello everyone, I'm Gavin Sri and I'm also electronics and communication engineering student of CST. So it's natural for me to know and think about those sensors. So I joined this session.
Hi everyone, my name is Shohei from Jomo Kenyatta University in Kenya. I happen to stay at the same hotel as Florian and Michael, so I decided to join.
That's a good reason. We share breakfast.
My name is Saad, I'm based in Singapore. I run a small little space there focused on assistive technology. I'm very interested in the DIY side, also active in the open science hardware community. So hoping to learn about quantum sensors.
Hello, I'm Kiran. I'm from India. I'm working as an assistant professor in the engineering college. I'm from the mechanical engineering background. I'm interested. I just learned about the computer and quantum computing. That's why I thought maybe it's something interesting. That's why I want to learn this.
Hello, I'm Suhas from India National Bank of India. I'm a lab manager there. So I'm an electronics engineer. So I used to have this. I work with ARS sensors, these ready-made sensors, and this one is a web making sensor. Right? So I'm interested.
I'm Thomas. I work at the FabLab of Catholic University of Louvain in Belgium, and I would like to see what quantum could do maybe for our STEM workshops.
Hello, I'm Raj from CST John, and I'm here to know how we can apply this or in the projects we are doing.
So hello everybody, I am Yos and I am from CST, currently pursuing electronics and communication engineering down at CST. So I heard this kind of sensor for the first time, so I'm quite curious to learn more, so that's why I'm looking forward to learn.
Yeah, very interesting people around here, very different origins we are all coming from, but yeah, to make this complete, I'm Florian Papproth from Germany, as you know, and I'm a computer scientist working together with my employer, Michael. He's a professor of mine, and yeah, we are in this quantum project, quantum sensor project. We are doing a research project with Germany, and base course we come later to. Yeah, and yeah, I'm working with Michael since 2010.
Yeah, and I'm Michael. I'm founded the FabLab in Germany in 2012. Yeah, and now we switch to this topic. I studied physics 30 years ago and teaching informatics, and perhaps as firstly tell you a little bit more about our FabLab, or we just show you a little bit, if we have internet, of our equipment. Just a flight through our lab. Does it work? Yeah. So first, there's my place. Yeah, you see. No internet now. Yeah. Hopefully it works. Okay. Perhaps not.
Oh, it works. Our family was only bench.
So
you need
yeah.
events
Yeah, I'm kind of impressed about this.
If it not works, I can tell you we are a FabLab connected to your university in Germany. We started in a very small room in the university, 150 square meters. Yeah, outgrown it very fast. Have a lot of attention from the local society and from our students. And yeah, with Michael gaining winning a lot of projects. We have the refund to grow, and this is why when we move to a large place, it's in Germany, it's related to a place where, yeah, lately we were coal digging.
So we have some 3D printers, as you see. Whoa! But all the furniture is done by ourselves. There also the area with VR and so on, and audio studio technology. There's a Fab Cafe with a really good machine, and there we have the area with.
We separated it in a clean area and a rough area, and this is where all the CNC stuff is going on. You have a wood cutting area. This is more related to laser cutting, and this the big box there is our laser metal laser cutter.
So there is a metal laser cutter, electronic area. So we think we have nearly everything.
But immediately after we changed to this larger place, we grow from 150 to 600 square meters. Immediately a year after, the place is getting to get a little bit small again.
Yeah, it is.
So, but that's who we are. We're coming from. Yeah.
So, and as a normal FabLab, we are open for everybody since more than 10 years. And now we are this quantum technology FabLab. And, well, what are quantum sensors of second generation? They use quantum mechanical effects of individual or few particles or states of these. And often this means to determine by means of electromagnetic interaction. And the most popular thing are diamonds. So you see a red diamond, and that is because of a diamond center. And this diamond center you can use to measure magnetic fields. And that at the end we want to show today how to do that. So, why? I cannot see now. It's stupid for me. So, why should we use sensors of second generation? The status now, it's an emergent technology, so there's no real product at the market. The first products will be there in a few years. So as we started the project, everybody told us, you can't do anything because there's nothing existing and you are stupid. You also want to do it DIY. That's impossible. Yeah? But why shall we do that? What do we expect? We expect that we might measure without calibration. A new kind of sensor without calibration. Yeah? But you know all these DIY sensors. They're really nice and you get a value. But you don't know if this value has any connection to reality. So you have often, or you should, calibrate them with a calibrated sensor, which is most often more expensive, and then you can use these DIY sensors. And these quantum sensors might not need to be calibrated. And the second thing is we will have unreached sensitivity and better signal quality. And the third, of course, we could develop completely new applications and smaller devices. For example, one idea is to be able to measure the magnetic field of our heart. So that's in the picotesla area. That's millions as strong as the Earth's field. Yeah? And if you are able to measure the magnetic field and the electric field, like you do now, you can you have better understanding of problems. Because if you just have the electric field outside, you cannot look in the heart. So you can see the currents in the heart with a magnetic sensor. And another thing, this you might know, that's in an electric cabinet. And if you twist these sensors around the cables, you can measure the current contactless. But what we want to do, we want to have sensors outside of the box, on the plastic side, and we would like to use machine learning to know which device is connected, and therefore we need new kinds of sensors to do that. And then, without opening the system, you can measure the currency or the power consumption in your home, your smart home, and can reduce it. That's the second idea. And there are several special ideas. You might know an atomic force microscope. So there is a very small tip, and for example, you have here a picture of a compact disc. If you replace this through a nanodiamond, you can measure the magnetic field in the nanoscale of the surface. That could be also useful. I will show later, perhaps. For example, what you can do with DNA, you can have ferrum as connector to the DNA. So you have a ferrum ion, and it connects to some parts, and then you can, with this type of scanner, magnetic scanner, you can scan the DNA structure because you can measure where these ferrum atoms are. For example, and there are some other applications you can only do with these new technologies. So, yeah, here's the tip. The idea that the tip is nitrogen-vacancy sensor, so part of this library. Okay, what is this workshop about? You learn a bit about quantum physics, you experiment with lasers, optics, phenomena like interference optical spectra. We built a magnetic sensor, which uses the fluorescence of the nanodiamond, and we use these systems. So this OpenUC2, that are these black parts, just get one. So they are molded now, but there's also a plan.
So then you can see the difference. And the one is molded, and the other one is 3D printed.
Yeah. And this now company, it's a startup, and they founded half a year ago. They are from the University of Jena. The FabLab was called Lichtwerkstatt, Light Workshop. And they built the systems for microscopy with these building blocks. And they want to do something like the Arduino of microscopy. So to have a very cheap but compact system, which is tens or hundreds as expensive as normal microscope systems. And of course, this is modular, and you can change what you want to do with it. And that is one part of the system we use. And the other one is one of ours. It's the more 3D bot system. We use it normally for we use it for robot systems.
On a good place this time. I'm blocking this guy. I'll hide behind you or something.
So I show you a small film what we do with the other systems. So these blue and yellow tubes.
One or two chairs for you.
So we use it to build robotic systems, and here's just a small film about that. So what our students do with that. So yes, there's building blocks and with electronics, and for example you build line followers or other kinds of computers. And so it's a combination of Arduino ESP and these building blocks more open than Lego Mindstorm, and you can enhance it by yourself. And we use it in embedded systems to teach students. And this year they made robotic systems for schools and also handouts for the teachers and the pupils to make the informatics subject more interesting. Yeah, more interesting. And that's the end presentation, and you will see that we are sitting on the sides and giving the notes.
Yeah, we always try, we give them the students the whole semester time for building the projects, giving their especially treatments, ask them what they wanna, in which direction their projects are going, and teach them individually. And at the end, we organize this like a small fair. You know, they have a table where they present with a poster, and every one of them have to present their projects. Also to the public, we invite some public people with it. And it's a nice touch that they have to not only build it for Michael and for me, so they present it for the public. And this is why the projects most of the time are a little bit more integrated than it otherwise would be.
So when we're teaching this, we just give should go somewhere in the beginning.
Of course, the presentation is for everybody of you is in the WhatsApp chat as well. So you can have a look at it afterwards if you don't get it right now.
So now, what we did bring with us are some laser pointers, and they are really bright, but they're in this low class, so it's less than 5 milliwatts. But it could be dangerous if you look in it more than a quarter of a second, and therefore we have some first actions. The first action is we built laser safety goggles for green laser pointers, just for these, not for ones with more power. Then we built red slide filters for our experiments. So you see there many slides, and there is red filter equipment. Then we built the diffraction gratings. That is this. We can build diffraction gratings. We could build polarization slides, and we need a slide with a hair in the middle because we will try to measure the thickness of the hair. So, and hopefully that's not too easy for us, for you, because many of you are know this topic. So it's just, we start at the beginning, and now I'm searching the material. Ja. Wo sind die Schwarzen? Ja, wir suchen die Laser. Die Laser, die hattest du. Ja. Das ist die Laser. So, there it is. Sorry. So, we did some laser cutting. Yeah? And I think the principle is relatively easy. There is some glue, there it is. You have, and there is something to cut. And you have to cut the red foil and put it inside, glue it together, and then it is perforated. It is perforated here, and it is perforated there, and so you can make your own laser safety goggles. Please just give it everybody.
And this is the first German challenge, because if you fail at the safety goggles, you are blind at the end of the course. No problem.
We just have a sign on the wall. Do not look into the laser with remaining eye.
Yeah. Well, in this room, everybody will be fine. The other room is blind.
So we expected 5 to 8 persons, not yeah. Perhaps we can serialize it so that one person could catch the red foil.
Yeah. And because we know everybody of you loves these free goodies, everybody who's building a goggle for himself can keep it with you. And tonight is because we are the coolest guy in town.
So you have to measure it a little bit. And we only have one knife, or one.
I want to make some of your diffraction rating.
Yeah, that looks also good. You can use it.
This is just for absorption.
Yeah, it's just it's for studio lighting. And it's good enough for that laser, so if you took 2, you don't see the green laser anymore, so you see it a little bit. Yeah? And I didn't test it at about 1000, was it 264 nanometers, because they use this crystal to double the frequency. And if they have not an infrared filter, it comes out of it. That's one of the. If you have a very cheap laser pointer, it could be that they also send
IR as well as.
Yeah, and I didn't test it. This
is frequency level.
Yeah.
Is it host? Like if you spin it around, will it make it a dot pattern?
Here, Lisa, I have another pair of scissors.
It's continuous. Or continuous enough.
It's listed as Amazon, or Alibaba, or...
Yeah, no, it's, I forgot laser lamp, I think.
The film.
So we bought it in Germany.
Yeah, maybe that
This one is waterproof. Which is the plus. Ah, okay. We could do
it doesn't?
Yeah, of course.
In the other lab, there's.
So, yeah, we just need a little time. Okay, we have 24 and the next 15.
So what is the electronics inside? What is the electronics inside this one? Because I don't see anything really printed.
Yeah.
Other sensors, so why do we need
We don't need this today. It's just part of the system, and I brought just a tenth of the system we have because I had didn't fit in my luggage. So the system is really huge. So you can build a special microscopes like a light sheet microscope, or they made the coronavirus visible. And the coronavirus is about 20 to 40 nanometers. So that's sub-wavelengths microscopy. That's a Nobel Prize. I don't know. Do anybody know how this kind of microscopy is known? There's a special name for this kind of microscopy beyond the upper limit.
So have you got a picture of COVID-19 virus? Have you got a picture of COVID-19 virus?
No, I don't have, but the team did it. The team built a microscope for less than 10,000 euro, and normally you pay more than 150,000 euro.
Wow.
Yeah, and even if you buy it at a seller, you can just do one thing. And this you can combine and make other things.
One more question. What is this PCB designed for? The one that is installed inside?
Yeah. You see, just one moment. Could you give me box below? Yeah. So normally you need that you have a stable system, and therefore you can put these blocks in the spaces so that you can combine it, and therefore there are these holes in that. I think that you mean you can stick it here. Yes.
Yes. But what is this circuit inside? I see a slit here. I see some kind of chip on this PCB.
Yeah.
Is this some kind of a sensor or?
Yeah. It's a photosensor. Just 2 or 4 megapixel cam. It's for the Raspberry Pi. So it's a part of a microscope. If you use it as a microscope, then that is a sensor for your monitor.
So this is basically the eye of the microscope.
Yeah, exactly. So it's one possibility, because they also do microscopes for less than €50 or $50, and then you use your smartphone as eye, because then you don't need any electronics. So you could combine them.
So besides those things like these last for today, what's the objective? Making a magnetic sensors.
Yeah. So we will learn many things about physics, and we try interference and try to get a spectrum and fluorescence, and in the end we will have a nanodiamond which is forced by a green laser, and nano is very small diamond.
What's the outlet?
Diamond.
So what is that? I'm not familiar.
Diamond.
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 Okay.
Okay, sorry.
Yeah.
Girl's best friend, you know. Girl's best friend, yes.
Girl's best friend. So what are we doing with diamond?
That is a sensor. So if you only want to learn about the quantum sensor, you should come back in 2 hours.
Okay.
And before we do easier stuff.
Okay.
Yeah. But in the end, we will try to build a DIY magnetic sensor. With a diamond. Yeah. So if you glue it with the sticks, you have to press it down nearly a minute so that it is fixed. So, shall we go further on while you are doing that? Because I wanted to start with some theory. For quantum to the second generation quantum sensor in introduction for non-physicists. Okay, so what's quantum physics about? Quantum physics is the study of matter, and energy at the most fundamental level on atomic or subatomic level. For example, with photons, electrons, spins. And in this microscopic world, particles behave differently from what we are used to know. And one of this difference, for example, is the Heisenberg uncertainty principle. So it's principle, not possible to measure the position and the speed accurately at the same time. It's principle impossible. So we cannot look in an atom and see the electron and know the electron is there, it has this velocity. Yeah, that's Heisenberg's uncertainty principle, and that has many different different, I don't know how to explain. And one other central aspect is that particles, for example the photon has this wave-particle duality. So sometimes electromagnetic radiation behaves like a wave with a wavelength lambda and a frequency. Sometimes it's like a stream of particles of individual photons with the energy h nu. So that means that the energy of a photon is proportional to its frequency. And a photon or a wave is always the same, and nobody really is able to explain that or to understand that. Yeah? And also, hard particles like an electron could behave like a wave. Yeah? We should think an electron is a particle, could not be a wave. But you can do the same as you do with a photon, like interference, you can do with an electron, and then it has the de Broglie wavelength, which is proportional or unproportional to the mass and the velocity. Yeah? For example, if you have an old TV, there you have this, in Germany it's called brown truth, and I think there's vacuum inside, and you force electrons to get a high velocity, and if it reaches the display, it makes a point. And if you have there a slit for the electrons in the vacuum, you have interference picture, like with photons and a slit, or like with water waves and a slit. So electrons could also behave like a wave. And now we will use light. We use green light at 532 nanometers with this laser. Yeah, so this is 532 nanometers. But we know a whole spectrum of electromagnetic radiation. So this starts with radio, television, radar, infrared, and then there's a small spectrum of visible light. And after that, there are X-rays, gamma rays, and so on. So ultraviolet, X-rays, gamma rays, and so on. And the only difference is the wavelength. And with the wavelength, or with the frequency of the photons, that energy, as higher the frequency, as higher the energy is. So energy of radio frequency, of television frequency of that photons, they are not dangerous for us. But if we have ultraviolet, this is the spectrum, is only dependent on the temperature of the material. For example, if you have this 5300 Kelvin, Kelvin is you can if you minus 233.15 is grade centigrade. So that's the temperature of our sun, and that's the spectrum of our sun. So if you have an object with this temperature, it has this part of radiation. So there is also radiation in the TV frequency. Yeah, but most of the radiations, the most amplitude, is in the visible spectrum. That's here, and also there's ultraviolet, and also, well, there's also X-rays you can measure. Yeah. And if the temperature is lower, for example, it's 1000 Kelvin, you only see a part of red and perhaps a little bit of green. If it's higher, you have this spectrum and so on. So if you buy a light bulb or a LED bulb, there are these temperatures on it. Yeah? The higher the temperature, the more blue it is. The less the temperature, the more red it is. Okay. Well, a question: why is welding gefährlich.
Dangerous.
So dangerous. Why is welding, you know, so dangerous?
I do it.
The combination of the heat and the light coming off when you actually press I think it's not a laser, but the fire against the metal creates a reaction in both smell, heat, and light that our bodies don't react well with.
Yes. So nearly, because the light is depending on the heat.
Yes.
And it's just the heat. You have more than 5,000 Kelvin. So it's this, and the part of ultraviolet is very strong. So just depending on the heat, you have a strong part ultraviolet light, and that makes your skin hurt.
And your eyeballs.
And your eyeballs, of course. And because it is, as I said before, you measured the temperature of steel with a light bulb in earlier times. Because if the filament bulb has the same color as the steel in the background, and you have calibrated it before, you know 5 volts is 1200 degrees. You know that the steel behind it has exactly 1200 degrees. Okay, what about this question? Could any object not radiate, emit a photon? Photons. Could any object not emit photons? If it has mass? No. It could have mass, that's not the problem.
Well, if you got it at 0K.
Yeah, keep it at 0K, that's the problem. So, if you keep an object at 0K, which is not possible, it will not send photons. Otherwise, if it has any temperature, this rule of Stefan Boltzmann, this rule says it will emit photons, so it will lose energy. That's one of the phenomena. Yeah, and again, photons means any radiation of any frequency. It could be radio frequency, it could be X-rays. So, and some more physics, I'm sorry. I told you this, that the energy of a photon is proportional to its frequency. As higher the frequency, as higher is the energy. And you know this rule, E is mc squared, that's Einstein. So what we can do, we can equate these two. Then we have this, mc squared is hv, and if we change it in this way, we have a mass. We have a mass of a photon. And the mass of the photon is proportional to its frequency. Okay, but what does it mean to have a mass of a photon? Is there anything we could expect?
You could start measuring the actual photon. You could start measuring the photon once you understand the mass of it.
Yes, you can measure it. For example, one effect is you know these. Oh, how is it called? You have a vacuum tube and you have mirrors. And if the mirrors reflect the photon, it drives around. And this is depending on the mass of photons, of course, and of the energy of each photon. So you can measure it by its impulse. But there's another effect of mass.
Gravity.
Gravity. So, okay, gravity of photons.
Bends the light.
And here's the answer of Einstein and what the people did in, I don't know, 1919. They had the eclipse of the sun, and they thought they see the star there, but in reality they saw the star there because the light the gravity of the sun was strong enough to force the light to go this way. So we can, you know that, I think, but I wanted to show you these connections between energy of a photon, mass of a photon, gravity. Because I'm fascinated by this phenomena, and once again, I don't believe that anybody really understands what happens, yeah? But I think it's really interesting. So, another thing. Yeah, that's a question to you. And well, here's water. And I just got a small bottle of olive oil. And hopefully I can do that. Okay, what's that? That's very
I could have brought you some. Big roll.
Must be oil. Must be olive oil or sesame oil or Kürbiskern, I don't know, another kind of oil. Then it works, otherwise it works not so good.
Extra virgin?
Extra virgin, of course. You can measure the quality of the oil with this. And what do we expect? So I have a green laser. Can we switch off the light? I don't know if this... So what do you expect if I put it into the water?
Reflects a bit fast.
Green, yeah? Yeah, okay. So I hope it goes. So if you take your goggles, you nearly don't see the green laser, don't you? But you see this red light, right?
Yeah.
Oh yes.
Yeah.
Seeing this.
But,
very good. Yes.
But why could a green laser be red now? Yeah? I think it's a cool effect. You can see it with your goggles really good.
I'm going to try this with my olive oil.
Well, that I didn't want. Okay. And you have this bitter part of the olive oil, and as more of this bitter part is inside, as more it glues red. And you use this to measure the quality of olive oil. But what I wanted to show you is the effect of fluorescence. Okay, it just works. So you know this classical picture of atomic model. That's the Bohr atomic model. It's the easiest imagination of how it works. You have several energy levels, and only a few energy levels are stable. You can explain it with the Broglie wavelengths from before. Only if the wave of the electron is closed and it not destroys itself, the orbit is stable. Yeah, and so you have here for the hydrogen atom, you have two stable levels, and if you have a photon, which the energy we know, which is proportional to its frequency, and the energy of the photon is the difference between these energies, you can shift an electron up, and if it falls down, it sends a photon with the same energy out. So if you can do this with a green photon and it goes back, it will also be a green photon. Yeah, yeah, that's because of the electric force. In the middle there is the core, there are protons, they are positive charged and the electrons are negative charged, and as like on Earth with satellites we need energy to put the satellites to the orbit, and if they fall down they get energy. That's the same principle. So that could be the reflection in water, could be, might be. You know. But there's also other possibilities, and this is this. You have the absorption of red line, and then there's kind of non-radiative transition. That could be that the crystal or the material gets warm. Yeah, physicists would say there exist phonons. Yeah, acoustic waves are particles, of course, as well, and they are called phonons. So we have a photon-phonon coupling, and that needs energy. So we have green here, and then lower frequency back, and that is, for example, red, because red light has lower energy. And of course, nothing of that is real. Yeah, that's a better picture of how it is, because we have this Heisenberg's uncertainty theory, and it's more like a statistical distribution of something. Okay. If we look in the sun and we get the emission from the sunlight, we will get this. It's a spectrum, but there are black lines in the spectrum. Do you know why? So why?
I have a question. I don't know why, but I have a question. Does it have anything to do with the darkness of space at all?
No.
No.
It's atmospheric composition. The gases in the atmosphere.
Yeah. Or?
So the question is why the black lines are in the spectrum looking at the...
Why are there black lines? Why?
The emission spectrum, right?
It's a spectrum you would see here from the sun.
So it's the atomic, so it's telling you what atoms are in the sun, yeah? Like what elements are in it?
Could be, yeah, could be. Or in the atmosphere.
Okay.
Yeah, that are called Fraunhofer lines. And if you look at the atmosphere, you have several materials in the atmosphere. The best known is natrium in the atmosphere, and it absorbs at 588 nanometers, and therefore there's a black line if you look through the sun in the atmosphere.
So that's the atmosphere of the sun?
No, our atmosphere.
Sodium in our atmosphere?
It's in our atmosphere. I'm relatively sure. Not absolutely.
Yeah.
So this is the same equation we use to quantify what other stars are made up of, right?
Once again?
To quantify what other stars are made up of. Let's say we are studying a star that is far away from us. We study this equation depending upon the changes that we observe from the sun and the changes that we observe from the star. Is it the same equation?
No and yes. So often you know how a spectrum of a planet or star should be, and I think you mean this Doppler velocity measurement, that for example stars which are more away from us, they have a higher velocity outside, so they vanish quicker, and you have this Doppler effect. So you know the acoustic Doppler effect if you have this yeah? So it's high here and low there. So if an object, a colorful object with a known spectrum comes through us, it's more blue or higher frequency. If it leaves us, it's more red. And that I think you meant that we could measure that.
Yes.
Yeah.
Based on that we can measure. So what I was asking was, based on the spectrum we know what is present in our atmosphere. So similarly, studying the light that is coming from the other stars, we can measure the components that the atmosphere of that star is made up of.
Right.
Right. That was my question.
Yeah. So what else? Okay. Then we have this phenomenon of coherence and interference of water waves in this. It's interesting that if you have water and you have two dippers and you dip in the water at the same time, you get waves. And these waves could enhance themselves if a wave if the wave top comes to another top. Here is the most difference in oscillation, and there are also still parts where the water is really still. And yeah, you can just through stones and water, and you see this interference. And of course, you all know that we could do that with light. So if we have a slit and we have a laser and we light the laser on a small slit, then we saw in the middle a high area, then a dark area, a light area, a dark area, a light area. And that is because of the interference of the light, because here there's no length difference, but here it's just one whole wave difference, and then it's positively überlagert. I don't know. Überlagert? Overlaid. Positively overlaid. And if you, for example, have half a wavelength difference, then the maximum amplitude is overlaid by the minimum amplitude, and then you will have no light. So that you all know, you know this interference. Interference. And my question and the next task is, how could we measure the thickness of a hair? How could we measure the thickness of a hair?
I'm going to attempt to answer again. Alright, so when you were talking about how light, like for example, light wave example, about if it goes in green and comes out red, then you know that there's been a decrease because of, I guess, how much ever thickness. So perhaps in that same way, if you send light through it, or if you send light through it and it comes out on the other side of different shade or different color, then you can measure, depending on the color that it comes out on the other side, how much thickness there was to change the color?
It could be. It could be. We could try that, but now it's another principle, and of course it's connected to that what we did before. Yeah. So
measure diffraction around the side of the hair, because you'll get you get the light coming from each side of the hair, so there will be some interference on the other side of the hair.
So a slit is the same as the hair. It's totally the same behavior as the slit. So what we can do, we can take a laser, and here is the hair, and we will have on the wall, so we will try to do that 2 or 3 times. On the wall we have our interference pattern, and if it is in an angel where the difference is one totally wavelength, we have a maximum, and otherwise we have a minimum, and so on. So this angel is the same as this angel is, and then we can measure or can use this formula because we have very small angels. Normally we have tangents and sinus, but if the angel is very small, you remember Taylor row, we can show it if it should be. So if it is very small, it's reduced to this formula. The diameter of the hair through the laser wavelengths, which is now 533 nanometers, is the same as the difference between 2 maxima through the length of the laser ray. So if we have the laser here, and we have our slide with the hair here, and we see the interference pattern there, we have to measure the wave from here to the wall. We have to measure how far is one maximum or the middle maximum to the next maximum, and we know the laser wavelengths, so we could
solve the equation
and know the thickness of the hair. And that would be the first experiment. And therefore we have all this equipment, and we have 2 laser pointers, and a too large group because we need somewhere a wall to show it, or because the group is so large, we do it less experimental, and I will show you, and we measure it. So perhaps it's better today. So, do anybody have a hair from me?
Any volunteers?
There you go.
This is how they steal your name.
Plenty of it. Yeah.
Oh, in a diaphragm, in the slide.
Okay.
Please. Just open the slide, put the hair inside.
Alright. I'll have those back later. How do we open it? Ah, there's a thumb thing. But yeah.
So where do we have the
Alright.
adapter?
We got it?
Yeah.
Yeah.
Let's just put it tight, close it.
Yeah. I think we got it.
Okay.
Great. Got it in there?
Yeah.
Alright.
There's a frame with a hair in it.
Yeah, my hair framed, yes.
Okay, do you have, there's a slide adapter? And do you have the adapter for our system somewhere? It's there, but we haven't. So it's also, no, it's also not. There's one lying there, this black one. Yeah, thanks. I don't see anything.
Where is it?
So it can be a building block.
Do you need to put it? Just put it in the slide adapter.
Where's the slide adapter? Oh, you got the slide adapter.
I'm just getting the waste material. It's just a 3 support.
Do you want pliers?
That would be helpful.
Oh,
Thank you.
Could I have the black one?
Thank you. How much pliers in the United States?
So, but okay, how do you do that?
Usually don't leave them
Yeah,
right.
because it's interfering. At first, just the fact, yeah, because we have no space. I'm searching for the hair. I don't know where it is. Was it in the middle?
Yep.
Somewhere?
Was.
Ja, that's no space left. Siehst du das so? Ich sehe es nicht. Oder ist es nicht mehr da?
Oh, it's gone.
Yeah. Story of my life. No.
There it's gone, so
I have
need
more.
a new one.
Get you another one.
I have a question.
Yeah.
So just wondering, you know how we did when we passed the light through the water and then we passed the light through the olive oil?
Yeah.
So does the color of the hair make any
Yeah.
difference to how the light goes, how the laser goes through it?
Oh. Yes. So before it was coherent light, and now we have fluorescence of the molecules of the olive oil. So it's totally different, and it's a totally different color. Well, don't know what more to say.
You asked for the hair.
Yeah.
The color of the hair makes sense.
Yeah.
At the color of the hair, so I misunderstood the question. Ah. So there you see the effect, right?
Yeah.
So normally I wanted to do it at that wall, but the problem is that everybody gets a laser. Of course I could turn it around. Yeah, but if I turn it around, that's stupid. No, that's stupid. So we have to kind of improvisation. We try to measure it. So we try to measure the difference. Takes a
This is...
So, Ms. Eimer, the distance to me, please. 2 meters, right, isn't it? It's inch and centimeters, both.
150.
150? Okay. We bought it here, so... Okay, I stand there.
It's around about 3 meters. It should be
3 meters. Now I try to make the interference picture there. So it's there now, but you don't see it. So measure please from the left maximum to the right maximum. The first left and the first right maximum.
the first left, the first right. Can it be 4 centimeters? From here to here?
Yeah, 4 centimeters?
Yeah. It's 3.5.
Okay, 3.5 centimeters. Now we need somebody to calculate. So we measure from one maximum to another maximum, so we need half of that. That means 1 point. Ah, there is happy something to write there.
There should be a marker.
Should be a marker. No.
I don't think so. Might be. There was probably on the table somewhere.
So we would measure, we would calculate 1.75 centimeters through 3 meters, and this multiplied with 532 nanometers.
So,
like real
1,75
ja.
geteilt durch 3
ja.
mal, wir haben grünes Licht, wir haben 532 mal 532.
310.
Das sind 310. So you have thin hair. Ah, he has thin hair. It's
is that guy.
That guy. Yeah. So it should be 31. It's a mistake. 31 micrometer. So it's 0.031 micrometer. Yeah. So. Yeah.
Amazing.
Yeah. Okay. You believe it. And well, that's a possibility to measure the diameter, for example, of a hair. You can also measure it from a dog. It's thicker by laser, and otherwise you cannot take a centimeter or how's it called?
Caliper.
A caliper?
Caliper.
Yeah, for example.
Micro caliper.
Yeah. Next question. I thought we didn't do that, but there is this grating, this grating. Yeah. And the idea was to also use this slides. I can show you once a time. And give me this black paper. The idea originally in a smaller group was to take this grading foil. There are 500 lines per inch, and we just take this, how shall I take it? Call it, can I have that? Vorlage, I don't know.
template.
This template, yeah. We just take this template to use to make it ready for the slide. So now it has the right diameter, and we could do it in the slide, and then we have this slide holder, and we can easily show what effects have this gratings, diffractions gratings to light. And I will show you, and you tell me before. So we had a slit or a hair. Now we have many slits. We have 500 on an inch, and we have a laser, a green laser. What will happen?
Make me wait.
Yeah, again.
So I'm thinking, I'm assuming that since it's going to be so many dots, it's going to look straight line.
So many dots on a line, or what?
Since it's going to be so many of the dots going across, it's going to look like a straight line.
Okay.
You're not going to tell how many individual dots there are.
Yeah. Could be other ideas? So I'm waiting for. I just do it. Okay. Okay. So what happens that we get individual points, and these individual points are depending on the light length, wavelengths of the light. Yeah, because the effect we had before is added. So we had a maximum here and a small maximum here. And now, because there are so many slits beside, these maximums add together, and and in the other areas the light is reduced. So what happens if we take a red laser pointer? I should have one somewhere. No, just yeah, this laser pointer somewhere. Yeah, den Präsenter.
No, it's the presenter, I think.
Yeah, just a normal presenter. Laid on the table, or it is inside this box, I think. Could be. Hopefully, yes. So, I have a red laser pointer, I hope. And I have a green laser pointer. I don't know if this fits together. So, how to do it? Does it fit? No, it does not fit. So, does anybody see that? So, can you mark the green point, please? For example, you mark it as you stand there. Okay, there and until there. And now I change it to a red laser pointer. We test this before. And it's there, and outside of him, it's more on the side there. Can you see it? And that's it behind the start with this. So because the wavelength is much longer, it's much more on the side. The green light is here, the blue light would be there, the red light is there. And of course the question is, could we use it to show the spectrum of a light source?
I think yes, if it's a fixed distance.
Yeah. So that would be the next experiment. We don't do, but what I do have, where do I have it? I just show you the principle, because it's, the group is a bit too large. I have different light sources. Should be one. Yeah. So this, for example, is a white LED, And then we have also a laser cutted slit for the slides. And then we could combine that, the LED, the slit, and perhaps we use some optics again. And then we see the spectrum at the wall. So that would have been the next hands-on experiment, but I think you could understand that. But what you can do also easily is you can have some light. For example, you have, I think you have, or you can look at the monitor. So normally you need a point. Yeah, you just need a point of light or a small slit. And if you look here, you can imagine the spectrum. It's too. Oh yeah. I don't know if you can. Do you see that? Or just a moment. No, where was it? No, where was it? Yeah. Can you see the spectrum? I don't know. If you, yeah. So that's a relatively easy way to have a very cheap instrument, only a few $, to show a spectrum. And of course you can enhance this. For example, you can have a camera and slide it to measure exactly the part of red, green, and so on. And of course, it works for all radiation. It works for infrared light. You don't see the light, but if you have a photosensor for that light, you get the spectrum of it. And you can do it for less than $10, the spectrometer. And
give it a roll, maybe.
Yeah, that's another possibility, and a surrounding to do that easily. So what's next? Yeah, that would have been the thing we have done. Okay, another thing of photons and of other things. Waves are polarized, or have a polarization. For example, if you do this experiment, you have Bohrmaschine, drill. You have a drill, of course. You have a drill, and you have some kind of band, I don't know. String. A string, yeah. You have some string. Then you have here a radiated wave, a circular wave. But if you have here this instrument, which has such a flat hole, after that you have only a linear polarized wave. In front is circular, then that is linear polarized, and you can also do that with such a foil, the plastic sheet. Yeah, there's also a plastic sheet for just, I don't know, €1. You could use the same instrument, cut it for the slide, and then you have, it's only one, then you have a polarization filter. So if the light now is, well, polarized in this way, and we change the direction of the polarization filter, it will be dark, and everything in the middle. And for example, if we use again our laser, at first it's polarized light, I think. Oh, it's not really polarized, a little bit. But if we try to put two after another, well, I don't know if this works. We can make it darker and lighter with two polarization filters.
You could try it on the TV if it's polarized.
Oh yes.
Ah, okay.
Why not?
It's a little bit. Yeah.
No, I think.
Yeah. So that's also one effect of light. Yeah, and now another thing. Do you know a Michelson interferometer? Okay. So what does a Michelson interferometer does? You have here the source of light, laser light. So laser light is special because it's coherent light. The waves of the photons are synchronized, so they all are in line, synchronized. And if you send a laser here and you have a mirror which lets half of the light, half of the illumination through, then the laser goes through that mirror, it goes back, and it goes to a screen. And on the other hand, the same laser light goes to the mirror, is reflected up to this mirror, and goes down. So, and then you have the interference of the light with itself. And it is interesting if you change the distance of the mirror in the area of the wavelengths, this picture changes. So if you have one wavelength more, one of the rings goes outside. So we have a measurement instrument for distance which is as exact or as selective as wavelengths. So you can measure in the nanometer scale. So we have millimeter is 1,000th to 1,000th of a meter. You have micrometer, what is 1,000th of a millimeter, and you have nanometer. And you can measure, for example, distances less than 100 nanometer with a Michelson interferometer. What to use it for? For example, a known experiment is that you have here a metal on that, and you increase the temperature of the metal, and then it gets longer. And you can measure this in the nanometer scale, for example. Yeah? Or if you have a very exact CNC machine, it uses that to know where the position of the drill is in the nanometer scale. It's one of the possibilities, yeah, beside others. Yeah, and of course you can buy that for schools or for universities. That's a normal kit from FabLab. It costs about $3,000. Yeah. Yeah, or you build it by your own. Do you have it? No. Where do you have it? Where is it? There it is. Wow. So that's the same for power.
5 Volt.
5 Volt. Hast du die da? So that's the Michelson interferometer, but for less than $100. So it's the same system, these building blocks of UC2. We have here laser. Let me think about. We have 2 lenses. Yeah, we have 2 lenses. We have, wow, this mirror. That's not good. We have here these mirror with reflects the light and also gives the light through the next mirror, and then on this side it's adapted, and if it is right in position we should see the interference pattern, but I have it in my luggage, so I don't think that is now.
Michael, I have a question.
Yes.
So usually on a Michelson interferometer, you have to have it very well aligned to see a pattern.
Yes.
And we usually use micrometer screws to get that alignment.
Yes.
Do you have micrometer screws on this?
Normal screws here, and hopefully I have this pin to do that. But you have to do it really exactly. But the last time I took it and get it out 2 weeks later, it still works. So that would also be normally part of the workshop, and we will try to do that. Ja, ansonsten habe ich auch die Breadboards mit dem Adapter und Powerbanks. So, but what I want to say, that we have a system with which you can build anything. And normally you have this in school, for example in school, and when it is defect, oh, it's here. Oh, it's not synchronized. So it's, yeah, it's, I don't know. So it's nearly good. It must be together. Then we see the rings. But I don't know if I have this screw with me. Hast du einen Leatherman in Sechskant, um die Schrauben einzustellen? No. Yeah, we could do that later, I think. I'll try a little bit. So you imagine the interference pattern. Yeah. So we have little screws here, so little 6. Yeah, but we would have to calibrate it. So, but in principle, we have a Michelson interferometer for less than $100, and if we want to have anything else, we put it on the table and make something new. And if something does not work or is broken, we go to the next 3D printer and print our materials we need. That's the idea. Because normally we will go in school with all this equipment. Normally you have one interferometer or one experiment, and you can only use it for this experiment. And if it is broken, you have to buy the new parts. And we would like to give this to small student groups, so that you have 5, 6, 7 interferometers. You can experiment by your own, and that's it. Okay, we make it off. So we can show you after. If you like to calibrate it with us, we do it in a smaller group. Okay.
Ja, sind wir im Fortschritt.
Gut, wieso?
Wir sind jetzt vor der Hälfte, das könnte auch Spoiler
So, I didn't thought that 2 hours are gone, but now 2 hours are gone. Do you want to have 10 minutes or 15 minutes pause to get a coffee or something like that, and after that we go on? Yes or no? No. No. Okay. There we go. Okay.
Excuse me, before proceeding, what are you using? Is it M5 stuff?
It's M5. Yeah. Only I improvise it because Michael asked me for have a 5-volt thing, so
but we take it for the sensor.
So just providing the power.
Yeah.
This was just
before you said that. Before you said the reason why we did second generation on quantum is without calibration. And why do we need calibration at this experiment?
Okay.
So what do you mean by calibration?
That's not a sensor. That's not a quantum sensor.
Okay.
That's classical stuff.
Yeah, exactly.
And you need the laser beams exactly be together.
Yeah.
And the focus was displaced.
And what calibrations do you mean without calibration?
For a quantum sensor, that it is an absolute sensor. So you don't need any calibration. It's physically absolute.
So just aligning the light.
And that are ideas until now, because once again, there are no real products now on the market.
Got it.
So now we come to sensors of the second generation, and to a thing which is called optically detected magnetic resonance, ODMR. So if you look at the papers, you find thousands of papers about this topic. It's the topic in the moment. Or how to build a quantum sensor of the second generation. Well, to remember you, if you have diamond is made of carbon. That's in the 4th row of the periodic system. That's a simple system. So it has 4 electrons outside for bonding with other partners. And nitrogen is in the 5th group, so it has 5 electrons to bond with the neighbors. And the thing we use for the sensor is a diamond. So that's the normal diamond structure, or the lattice of a diamond. So we have 1 diamond and 4 arms through other diamonds. And we take this diamond, normally an industrial diamond, because diamonds on the street are not pure enough. So we have an industrial diamond, and then we try to put nitrogen on the surface or in the diamond. So that's, for example, called chemical vapor deposition. So there are several possibilities to do nitrogen in this lattice. And what is built there is called a nitrogen-vacancy center. So we have 1 electron more, and there is something like a hole, and that builds a system together. That's the idea. In reality, we don't really know what happens there, and it could be shown that 7 electrons are used to do something, but because of the Heisenberg uncertainty theory, you cannot look exactly through that. You cannot really measure it. We do not really know what happens. But what we know, if we have this nitrogen vacancy sensor, we can send green light on this quantum dot, and we get red light out of it. And that we can use for sensor. So where can we buy it, or what could we use? That are normal diamonds from FabLab. They are 3 millimeter long and 3 millimeter, and I don't know the height. I don't know it. And they have 300 parts per billion of this nitrogen vacancy centers. More exactly, it's NV minus centers. There are different kinds of centers. So that are pretty much, or you can also use some with less nitrogen vacancy centers inside. So you can buy that for $1,300, for example, this crystal. Or what we do, but I just wrote the company down. We can use nanodiamonds. So if you saw this diamonds, there are splits, nanodiamonds falling down from it, and you can buy, I think it's 1 milligram for $300. But 1 milligram are many nanodiamonds. And then 1 part, which you can use as a nanodiamond, is about $1. And these parts we are using to build a demonstrator sensor. So we glow these parts. Yeah, there it is. Yeah. Is it that side, right side? No, it's the wrong side. So we use these diamond sensors, and now I would like to show you from a paper the simpler way what to do with it. That's called microwave-free magnetometry with nitrogen vacancy sensors on diamond. And I just will talk about the effect. So you give green light to it, and then you have these processes inside, and it has red fluorescent light. It's the same as with our olive oil, therefore I showed you the olive oil. In principle, it's the same. And the brightness of the red light is depending on an outer field. So if you take a magnet and you lower the distance to the nanodiamond, the red line gets darker, and if you put it away, it gets brighter. That's the easiest way to use this diamond sensor. Ah, it's amplified. Oh.
Glued onto the...
Ah, okay.
Maybe we can show this at first.
Yeah.
Before I put it again.
So
we have here, normally it's onto the XY stage, but it fell off. It's already glued on it. But these are the sample with the diamonds.
Yeah. So this is a PCB, and I will explain the next kind of measurement after that. There's antenna on it, and here we glued nanocrystals on. So just
What kind of glue did you use?
I don't know. It's normal glue. It was I think. Just normal glue. You have to pick the nanodiamond and put it on, and before you have to look with the laser if it's gluing red. That's all. And then we can take it in our system, have a red filter and another red filter, and have a photo detector, and can measure the brightness of the red light. And that's in principle all for the simple system. What we also do, we have a lens system in between, because the diamond is in the focus of the first lens, and then we take a second lens, and our sensor is also in the focus of the second lens, so that we have all light of the nanodiamond and bring it in the sensor. Oh, sorry. Yeah. Okay, he tries to do that. So, and the sensor, it's just a normal IC, it's a OPT1Nil1. It's a photo sensor with an amplifier inside. So it just needs a resistor and a capacitor, I think, 3.3 to 30 volts, and then it has an output signal between nil and 3.3 volts. So after that, you just need any device with an ADC. For example, we use this M5 stack. There's an ESP32 inside, so you have a 12-bit ADC. So in your software, you have an integer number between nil and 4095, which reflects the brightness of the red light. So, and if you take the magnet to the diamond sensor, there's a dip, and the depth of the dip is proportional to the magnetic field. Yeah, that's the easiest way.
Maybe you can show the diamonds on it. If everybody put the Google on, we can
So,
show the
exactly.
diamonds are on it.
So, yeah, please. Yeah, both sides, please. Do you have glue it? Well, I've also a good one somewhere.
Der Filter oben drauf, der reicht nicht, oder?
Ja, reicht auch, wenn man von oben guckt, ja. Ja. Also, deine Brille ist natürlich immer besser.
Ja. Warte.
So without glasses you can't see it, because you only see the green light. With glasses you should see the red line.
If you can have a look now at the stripe on this, and I go over it with a green laser, you see that the NV centers are glowing red, and these are the small particles which are on here. And that is what we try to point at. It's a little bit fragile.
Yeah, do you see it?
Yeah, and there are only not one, because we throw some powder on it and glue it on, so there are more than one center on it.
Yeah. And Florian has the right glasses, because they're not in any green light, so you can see it much better with that glass. So what my idea is, I now show you the rest of the theory for the better measurement method. You make a pause, and when you come back, we have built the system here. That would be my suggestion. Is it okay? Ich zeige jetzt noch ein bisschen Theorie und dann machen wir Pause und wir bauen es auf, so dass man. So, a bit more theory. Wollen wir den Sensor? Hast du noch in der Hand? Kannst du mir noch mal geben?
Den Sensor?
No, das ist den Diamantstör-Sensor.
Das wollte ich sein, nur.
Achso, hast du das gekippt?
Ja, das ist auch.
So, the thing we did now, nearly nobody does, but there is a better way to get the magnetic field. But what can you use this for, what we did now? You can also take a glass fiber and you can glue the nanodiamond on the glass fiber, and then you use the glass fiber to do that. So you bring green light in the glass fiber and you get red light back, have a filter and measure the red light. So you have electrically free measurement of electric fields, because magnetic fields, because normally you need some kind of coil to measure magnetic fields. How is the sensor called? It's too long. Hall sensor, some kind of Hall sensor, of course. Yeah, but that are all electronic components. So if you try to measure the magnetic field of 1000-degree hot steel, for example, you cannot use the electronics. But you can use a glass fiber and a diamond, because 1000 degrees is nothing. So, for example, one possibility is to measure high temperature magnetic fields with a diamond sensor, for example. Yes, and there are other things we might pretend, so I won't explain it to you. But there are other possibilities which nobody thought about until now. Okay, but the rest of the world is trying this type of measurement. It's called optically detected magnetic resonance, but with a microwave field. And therefore that's for the microwave field. We need a field between 2.4 gigahertz and 2.8 gigahertz. And we need something like a near field antenna, that is this part of copper there, where we glue the nanodiamonds, because we need the field at the nanodiamonds. And well, what happens? I try to explain it. That's the energy level system of the nanodiamond, of the nitrogen-vacancy center. And we have here the ground state, and the ground state is spinless. So it has no orientation. And if we put here energy, photons, but photons of microwave length, 2.5, 2.6 gigahertz, we can level up the electrons to these states. That's -1 and +1, that's the direction of the spins. And this forces another behavior of the processes after that. So then when we have this in this level, we pump it with green light, it goes up, and red light goes down. But if we have resonance here, so if we fit this or this resonance light, the red light is less than before, because the probability to go on another ray is greater, larger than before. So I explain it with the effect we see. If we don't have any outside magnetic field and we change the frequency from 2.4 gigahertz to 2.8 gigahertz, we get one dip, only one dip without field. If we have an electric field, we get two dips, one at a lower frequency and one at a higher frequency. And the distance between these dips is proportional to the outside magnetic field. And that is the measuring method. We have to find these dips, we measure the distance, and we can measure a magnetic field in the nanotesla or below nanotesla area. Yeah? That's also the simplest way. Yeah, after that, it gets more complicated. But that's the effect. So we have a magnetic field, therefore, classical model, we have electrons and they have a spin. So they have also a magnetic field. They interact with the outside magnetic field, and one level is shifted, one level is downshifted, and therefore we have the energy shift here through the magnetic field. So on a lower level, it is on a lower level, the electrons are able to go to this level, and we get less red photons. And on that level, the electrons are able to be shifted, and we get again lower emission. So that's a reason for these two dips, and well, just have to measure the distance. That's all, in principle. Did you understand? So in reality, you have to read some papers because it's a lot more complicated than I try to explain. But did you get the principle of it?
Can I ask
Okay.
the y-axis? What is that?
That's the energy level.
Energy level. So
That's like the simple model before.
the right-hand side, the graph.
That's a measurement curve of our photosensor.
Photosensor.
So this is the lightness, how light it is, how bright it is, on this axis, and this is this microwave field where we change the frequency. Yeah. So we have an outside field. We change here the frequency, and with our photo detector, we measure how bright the light is. The frequency gets higher and higher and higher, and then we have a dip. The light is less than before, and another dip, the light is less as before, and the distance of the dips gives us the height of the magnetic field.
So you vary the frequency,
Yes.
and you measure the intensity.
Yeah, exactly.
So how fast it is? Like you have to vary the wavelengths.
That doesn't matter. There are different methods to measure. For example, of course you can use an oscilloscope to measure the amplitude, and then you have to be fast. Yeah, so you measure 10,000 times a second. But you can also just go slowly forward, look if there's a minimum. That depends on your sensor and what you want to do. Yeah?
But in easier words, it's a pattern which is visible on the sensor side with its two dips, and the distance between those dips is a you can directly point onto the strength of the magnetic field that is causing the dips.
So in principle.
The distance of the dips is changing, and then you can calculate the strength of a magnetic field. That's what makes it a sensor.
Yeah. So, yeah, other questions? So that's a picture for one nitrogen-vacancy center. But one center means one photon in and one photon out at the same time. So you won't see it. You need more. There are several hundred thousands, no, I think more millions of nitrogen-vacancy centers in our crystal. Otherwise, it would not be bright enough. Yeah, and that's a problem, because we have this lattice, and every C atom has 4 bindings, 4 orientations. And this nitrogen-vacancy centers can also have 4 directions. So each center has other direction of measurement of the magnetic field. And because they are randomly in our nanodiamond, we don't get 2, but we get 4 dips on each side for the 4 orientations of this nitrogen-vacancy centers. And that makes it more complicated in reality. So that's the simple idea, but in reality it's more complex. But I also show you, the theory behind that is the Zeeman effect. I won't show it now, but I won't show you the experiment we did, or our colleagues did. That's their experiment with these, with these elements. So, where to begin? You have a laser, it's a green laser. You have a mirror, an objective, and you focus it at the nanodiamond. The light goes back through the mirror, on another mirror, on a photodetector, and the signal is shown on an oscilloscope. On the same time, you have a microwave voltage-controlled oscillator, which goes from 2.5 to 2.8 megahertz. They used 13 hertz for the whole round, and with that you have this small antenna and the microwave field for the nanodiamond, and then you see, if you synchronize that on the starting point of the wave, the microwave, you can see the signal on an oscilloscope, and out of these dips you can measure the field. And in reality, that's the thing that's made from our colleagues from university and Applied University of Münster. They also use the set, and they did some didactic elements so that you can better change it. Yeah, photodetector, laser, our nanodiamonds, the magnet. You change the magnet and you see it on the picture. That's all. What we want to do is, sorry. What we want to do, we want to integrate it furthermore. You see it here, and we ask us, if I take a very bright green LED, this is one with 49,000 candela and 10 degrees angel, is it good enough to illuminate the crystal, and just don't we need beneath the photosensor and the crystal a red filter? Then we could have here the microwave plate with the diamond, here the LED, here the photo sensor, and in between we do the filter, and then we have, somewhere we have it, then we can stack it at a device together to be some kind of didactically, so you can open it. Yeah? Or, to make it cheaper, why don't we use our phone? Why shouldn't we use the camera of the phone? The camera is able to have 360 frames per second. What was it? The actual.
We looked that up. It was fast enough.
Yeah.
In a special mode, it is fast enough to recognize it.
So a few hundred frames per second. We have the red filter. We have the nano diamond glued on it. We put the voltage controlled oscillator inside, and we give the green light again with a small laser and a fiber, or with a laser diode, and we just put it on our smartphone and can show the effect in the classroom. That's one of our next ideas. And that's it. Many thanks.
Yeah.
So, if you are able to, we would like to ask you these things. And to be honest, of course, honest feedback, open discussion.
But for a quick roadmap, so everybody knows what's coming up next, we really are interested in the feedback of yours. So that's why we think about some questions. Afterwards, we would really like to have a picture of you with everybody with his self-filled goggles on. And maybe we take a bio break after this, and then everybody who wants to come back, and we build up maybe a smaller group or with all of you, it doesn't matter. We build up this experiment because it's a little bit tricky and fragile to build up, and we see the effect on the M5 stack. Yeah. So, but this is a roadmap. Please, honest feedback. So we like to, and then the picture, and then a break.
Yeah.
Then we return.
Yeah. So, well, was our workshop motivating, and did you learn something? Did we match the right level? Have we lost you? Did you get the relevance of quantum sensors? What's your opinion about our quantum optic kits? Would you be interested as a FabLab to use it? So,
I just have a question, sorry.
Ah.
Could this be the beginning of trying to find new sensors for different things in the quantum level? I mean, instead of only magnetics to measure other things?
Yeah. There are a few ideas where to use this quantum sensors of second generation, and with this sensor you could also measure temperature and pressure, for example. But there are that's the most famous sensor kind, and there are not many other things on the market or in the research now. So we have to wait a few years to get new kinds of sensors. But as I showed before, you can use it, or you use it now, for vice versa. So you can also use nanodiamonds to connect it with organic material, because diamond is not poisy at all. You can take that and taste it. It's not poisy at all, and all organic material has carbon in it, so you can replace it by a nanodiamond structure, and then, for example, you can see by the fluorescence the behavior of the cells. Yeah, you can look, for example, for this. How is it called? The motor which makes the ATP synthesis. This natrium, kalium. Okay, you can see cell operations by using nanodiamonds as a sensor in the cell, for example. And there will be many different things to happen, to expect. Yeah.
I have a question about second generation. What is first generation? What is the difference?
Fourth generation was if you have not just one quantum dot or a small area to use as a sensor, but a classical effect, a larger area. There are also many interesting things. For example, do you know that you can measure with a fiber and light the temperature for the next 30 kilometers in a distance of 1 meter? Just to the light there, glass fiber, and you know here it is 30 degrees, 31 degrees, 28 degrees. That would be a classical effect, classical photon coupling effect, because it's not just a small, not a nanoscale part, but there is a whole region included to do this effect. Yeah?
So I have a question. All these experiments that we carried out today, and also the ODMR that we saw, is very similar to the fiber optic communication kit that is widely used today. So even the ODMR is very similar to the OTDR that we studied in our college. It is an optical time domain reflectometer.
No, what I told you is that. Yeah,
okay.
Yeah, but that's another fact.
So my question is based on that. Can this fiber optic communication kit that is used to deploy communication systems everywhere be used as quantum sensors? Because the working is so same, they work on the same principle. Because the ODMR also works on the basis of photodetector. That's what an OTDR does.
Yes, but the principle is totally different. So, okay, we use a photodetector to get the sensor information, or to get the information of the sensor, but it has nothing to do with the communication at all. It's a different...
Yes, I agree. I am not asking
Okay.
about whether we can use it with the communication system. I am asking the equipment that are used in the fiber optic communication work on the very same principles. So
Yes,
can
yes,
those
yes,
equipment
yes.
be used
In
here?
principle, yes. But for telecommunication, you use other frequencies. So if you have monofibers, you need the right frequency. So that could be a problem, but in principle, yes. And one thing to mention more, I have some, it doesn't matter. Perhaps in some times with this nitrogen-vacancy centers, you are able to build room temperature quantum computers. Yeah? Because if you be able to realize two NV centers laying side by side, you can entangle the atoms, or you entangle the spin of the protons, I think, but you can measure it with the fluorescence and the Wechselwirkung. The Wechselwirkung in German, in English, I don't know. It couples to the outer field, or the spin of the electrons couple through the spin of the protons, and with that you might be able to measure the orientation of the inner qubits. Yeah. So you know, if you now build a quantum computer, you need very low temperatures, a millikelvin or something like that. And the system to use, for example, ions, which are ions, for example, it's just a small area, but the whole machine is very used, and to get this temperature and so on, you need much energy. And if this goes further on and works, you could, in principle, have that in your smartphone at room temperature. In principle, perhaps in 30 years, yeah? We don't know. But many researchers research on this topic. So if you look at Google Scholar, you have 20,000 papers in the last 3 years about this matter. So, would you like to give us some feedback based on that question? So we honestly would like good and bad feedback.
Well, I think I like when you explain it that you also give some experiments. So it's very interesting on that. It's not really boring.
Thank you.
Yeah.
Although the group was too large, we would have liked to do it hands-on.
Well, yeah, for example, the slit experiments, I've never thought that you can measure the thickness of the hairs.
Yeah.
I learned it just the double slit, that kind of things.
Yeah.
So I really enjoy and learning something.
Thank you.
What was the level of your, everybody of you come here with a different pre-knowledge, so and some of you maybe more to the topic than others. You try very hard to make suggestions. It was quite nice. How was it for you? Is it a topic could you follow these all the descriptions Michael was made, or?
So I did get lost on the resonance slide. In fact, can you go back to that slide? So these guys understood exactly what was going on. But but the energies, go back. You passed it. Yeah, right there. So on this one, it looks to me like those two red transitions on the right. They look to my eyes like they're the same distance. The distance here is the same as energy, correct? And energy is the same as frequency, so you expect them to be the same dip. So those two, I think you need to exaggerate the fact that those two transitions are different in length.
Yeah.
In order for that to make sense on the double dips.
So normally, if you don't have this wave, you are in ground station. So you have an S orbital, which is not depending on this magnetic field. Yeah. But if you have this transition to -1 or +1, then you have the Zeeman effect, and it is you have two levels depending on the magnetic field. And then comes the green laser, and there is a difference in the probability to go down then. And
so it's not those two red paths that are
no. It's a sideway. It's non-radiation
detour.
Yeah. So the behavior time in the upper level is longer than. Yeah, that's what was the effect, I think. Yeah. But there are some papers. And even for that, what I showed with our experiment, we have a paper of 10 pages or something.
But this could be made simpler. Like all you'd have to do is show this is without resonance.
Yeah.
Fluorescence.
Yeah.
This is with resonance. Detour. Right. And this is the first energy. Drop.
Yeah.
Here's the second detour energy drop. Different path lengths, different energy amounts, different frequencies, and then I think that makes sense.
Different probabilities or different. Yeah. Right. Thanks.
No, I was going to say the same. I mean, this is like
this is hard to understand. Yeah. And normally you have 1 or 2 pages to explain exactly what it is, and of course you couldn't know this notation and so on. That's physics in the 5th or 6th semester. Yeah. That's it. That's bracket notation, Feynman notation. It's hard physics stuff, and it might be that I explained it bad. But what do you think about the way to go there? Because we started very simple. I showed it with olive oil. I showed the effect, and the effect on the diamond is the same. If I started there, you wouldn't have understood nothing. Therefore, I made many parts of physics, like the energy of a photon and so on, to come to this level, and also to show you some motivational effects. So, yeah,
Yeah, I loved all of the demonstrations.
Okay, it was very interesting. I mean, I was studying 2 hours.
Okay, that's good.
Yeah, so coming into it, I was really excited when I read about it and I read the description online. So I definitely wanted to come and attend because I've never had the opportunity to be in a classroom talking about quantum anything. So I really wanted to come in and just gain some sort of an understanding. But I really do love the way that you presented to us and with the olive oil and the water and all the rest of that. And you didn't really shame me for like giving my answers.
Hopefully, yeah.
Yeah, even though I had no clue what I was talking about. You know, but I did feel like I was gaining and understanding. And so of course, had you started there, I would have had no clue what was going on. But I do feel like now, if I go home and read some papers, I rewatch the videos, rewatch the slides, I really do feel like I could go home and actually attempt to put one of these together myself.
Cool, thanks. Great.
I would love to follow this workshop again with the hands-on experience.
So next time we will have more, and our idea is to have 100 places in Germany where you get this, where you have this stuff for schools and so on, and therefore we ask you, what is your opinion about this kit? Yeah.
Well, since we're a neighboring country, I would like to experiment with that. So I hope we can stay in touch.
Thank you. Yeah, it's a combination of open. Yeah, it's open source, but also available. So you don't need to print 1,000 hours. You can also buy it. That's the idea. We want to do both. And the black ones, that's UC2. The startup, they are on the market since half a year, and they are project partners.
So that's what our next roadmap is. It's at the moment it's that really experimental kind of stuff where we put these experiments together. Various parties worked together to find out what's the best way, what is the best cube system to build these experiments so that they are more reliable. And but we documented it afterwards. There is a didactic stuff is coming online. You can learn it. You can put it out for the teachers to make this test with their students or pupil. And all this stuff, all these cubes, you can almost do it yourself. You can buy the diamonds, the microcontrollers by yourself. That's why we presented it also here at the tech conference. But our ideas and what we're starting next year is the next project when we are finishing these experiments. We put together two flavored kits. It's like a normal kit, an advanced kit, and we put it out at the cheapest price point we can offer. So I don't think it's there's nobody involved.
For example, we try injection molding because we need 10,000 of them, and we tried by our own, and we want to reach 10 cents per cube. That's our.
Then we have put together a set which is more easy to get, and the first step is to spread that out to 100 test locations. You can give us a feedback, and then afterwards it should be, when everything's went fine, should be available as a free or a pre-commercial kit, what you can prepare more easily.
And the practices really. I mean, you can buy the practices for school.
You can buy universities.
Yeah, for example, but you will sell not only the cubes but also the teaching lessons.
Yes.
Yeah, of course.
Combination. Yeah. That's why we work.
The pages in the presentation. The web page is the presentation.
Yeah, it is.
We would like to that you stay. Maybe you can just in the WhatsApp group, so we can update you in the future about the process, and maybe if you have students or pupils by yourself, maybe you can be one of the 100 test sites. We put that kit out to test.